So let's say we have an electric field. Let's set up an electric field between two charged plates. And the magnitude of the field is given by this capital E. So we have an electric field between two charged plates. And we put a point charge in it. So we'll put a charged particle in it. Our charged particle is Q. So here is Q. It is equal to plus 1 unit charge. Okay. So the force that's felt by the charge is proportional to the strength of the field. So force is equal to Q times the strength of the field. This is force felt by the charge is proportional to the strength of the E field. And then if we recall, what was our original OG definition of work? It was the very first one we ever defined on day one. Force times distance. Force times distance was our original calculation of work. This is a force, so I can plug this in for force. Okay. This would be the integral of force. I'm going to plug this in here. Over some distance, infinitesimal displacement, dr. So then this is equal to the integral of the charge times the field times, with respect to position in the field or displacement within the field. Okay. Why did I put a negative sign here? See if finishing this relationship helps. So I have work. I've now set this equal to delta U. There's no heat involved here. We're not talking about heat, first law, so we're only saying that work is equal to change in internal energy, delta U now. Okay. What do I expect to happen to delta U if I move with the field? It would go down. If I move with the field, I would expect internal energy to decrease. And so in order to make that happen, I put a negative sign in front. Alternatively, if I were to move sort of against the field, I would expect that to take energy or raise internal energy. Okay, so there's moving against the field versus moving with the field. Work is equal to, because of first law and there's no heat involved in this scenario, it's just equal to delta U. This is equal to the electric potential energy. This is equal to the kinetic energy. Okay, there's a figure on the slides that I'll populate that hopefully helps clarify that a little better. It talks about, it sort of relates it to if I had like a ball rolling down a hill, the kinetic energy change would be given by the gravitational potential energy change as it moved down the hill. This is sort of similar as it moves in the field. The change in potential energy due to the electric potential energy component is just related to that movement in terms of KE. So I can write that work is equal to, again, I'm just going to go back to this relationship here. Negative the integral Q E PR. I'm going to sort of pull the Q out. If I move from sort of here's E1, here's E2, and this is my distance that I've moved here, this is going to be given by the difference in my potential or my voltage difference. And so this just becomes Q delta E if I integrate across this distance. And this is equal to delta G. So the work I'm doing moving this charge in the field is related to free energy change. Now, one of the things that's kind of frustrating, and then just remember that we already saw somewhere I wrote this as well. I could write it like this. Okay. For redox reactions, what's the sign of our charge? What is the charged particle that's moving? More loudly. The charged particles are electrons, okay? So they have a charge of -1. Here I'm letting charge be equal to lowercase nu times F, where F is Faraday's constant. Okay. 1 farad is equal to Avogadro's number times the charge on an electron. So this is 6.022 times 10 to the 23 electrons per mole. This is 1.602 times 10 to the -19th coulombs per electron. So when you multiply these two things together, you get approximately 96,500 coulombs per mole, and this is mole of electrons. And then nu in this case, in this particular equation only, is the number of moles of electrons being transferred. In our chemical reaction. So if I plug this in here for delta G, I write delta G is equal to negative nu times Faraday times delta. And the negative sign is again because I'm talking about electrons here. So that's maybe the first new equation that exists on your sheet that we haven't utilized yet. Under standard state conditions, this relationship is still totally valid, totally holds. I'm just now defining a temp, a pressure. I'm saying I'm talking about 1 moles of things. This would be equal to negative nu farad times standard potential difference. And the other thing that I can set this equal to is negative RT, the natural log of KEQ. And that's because we already established this piece being equal to this piece in chapter 10. And so I can rearrange this and say that the standard potential energy difference, or standard electrode potential, is given by RT, the natural log of KEQ, divided by, and the negative signs have just become positive here. Okay. And what this basically tells me, if you measure the standard potential difference, so if you measure the standard potential difference of your electrochemical cell, you can readily calculate your equilibrium constant. What were the other ways that we said experimentally you could get equilibrium constant before? Use a computer simulation is always the final answer, and there were two other things we talked about for measuring concentration. Yes, Rena. You could use an NMR spec, and the last one was some sort of light spectroscopy, an absorbance measurement or a transmittance measurement or whatever it was through your solution. So now what we have is I can set up an electrochemical cell, I can get a standard potential and use that to calculate equilibrium constant. Alternatively, what we will later show is we could measure concentrations of an actual reaction in an electrochemical cell and figure out standard potential. Either way.